Okay, so we are going to look at how to find the length of an arc described by parametric equations. And to do that, we're going to use Pythagorean theorem. So you know the Pythagorean theorem. The Pythagorean theorem says that if I know x and y, that length there, well, you know what that length is, right? You've done this a ton of times. This length would be x squared plus y squared. Well, the idea of finding arc length is exactly the same. So what we want to do is let's say we wanted to find the arc length from A to B. Really what we're going to be doing is just thinking about some point on that curve. So let's say like this point right here. And at that point, what we can find is the change in x with respect to time. So the change in x with respect to time, it's some little positive distance. So we've got some little dx dt. And then we've got some dy dt. And if we think about adding up those vectors, what we get is the arc length. And now it might be helpful if we add the vectors in the correct manner. So typically we like to do tip to tail. So let's imagine taking this dy dx and putting it tip to tail. Let me put the graph back together, so what we're going to do is we're going to add up dx dt and dy dt. So we're going to add these vectors, dx dt, dy dt, and when we add those vectors, what we get, well, what is that green area, or sorry, that green length doing a very good job of approximating? Well, that's approximating the arc length of the curve. So what we see is if we add the dx dt vector to the dy dt vector, what we get is the arc length. But the way in which we add vectors, and I know that we haven't spent a whole ton of time dealing with vectors yet, but what we've created is a right-hand triangle, and so that little length we'll call that little length dl. That little length is just the square root of dx dt squared plus dy dt squared. That's that one little length dl right here. And I want to add up all of those lengths from A all the way to B. So if I want to add up a bunch of little lengths from A to B, that's integration. And the equation is right here, but just so that we can see, we're going to be integrating from A to B all of those little lengths, which are the square root of dx dt squared plus dy dt squared. That's the arc length formula. Simple. Okay, so let's do a couple problems, a couple practice with that. So we want to find the arc length of this curve defined by the following parametric equation. And we want to find the arc length over that region. Now, it might be worth going and getting a graph to see what this looks like. So let's do that. If we pull up our graphing calculator and we want to graph, well, we got to change it into parametric. And we're going to graph e to the t cosine t. So times e to the t. And there we are. So we want to graph this. Let's change our window. We want to go from 0 up until pi. Let's step how we are. Let's take a graph of this. Whoa, that's a cool curve. I'm not sure if I see all of it, so I'm going to move. Does it keep going? Interesting. So here's our graph. And so that's what the graph looks like. But to find the arc length from 0 to pi, well, let's take a picture of this so that we have it. Cool. So to find that area, what I'm going to do then is find dx dt. And so we're going to need to use our the chain rule. So dx dt, or sorry, the product rule is e to the t times negative sine t plus e to the t cosine of t, and dy dt, well, dy dt is e to the t cos t plus e to the t sine t. Interesting. And so the arc length would be the integral from 0 to pi of the square root of dx dt squared. So e to the t times minus sine of t plus e to the t times cos of t squared plus, and this is kind of running out of room here, so plus e to the t cos of t plus e to the t sine of t squared. Now this is going to turn into a nice little algebra experience for us, but I think it's going to simplify pretty nicely. Okay, so we have a little bit more space now to do this. So to do, what we need to do now is expand this. And when we expand it, it's going to get kind of ugly, but then get really pretty quickly. So this is the integral from 0 to pi. And I've got two binomials squared. So this one and this one. So doing the blue first, I'm going to get, well, e to the 2t sine squared of t plus e to the 2t cos squared of t minus 2 e to the 2t sine of t cos of t plus, now that's the first, that's the blue one, that's I think dx dt squared, and then plus e to the 2t cos squared of t plus e to the 2t sine squared of t plus 2 e to the 2t cos t sine t. And remember, this whole thing is square rooted. And then at the end there should be a dt. Well, this is going to simplify nicely. This crosses off, that goes away. And if we factor out a e to the 2t, I have the square root dt of e to the 2t times sine squared of t plus cosine squared of t plus cosine squared of t plus sine squared of t. And you know, the mathematicians love the famous sine squared plus cosine squared trig identity, and so we can rewrite this as from 0 to pi. Well, this is 1 and this is 1, so we have the square root of 2 times e to the 2t dt. Separating that, we get 0 to pi of square root 2 times e to the t dt, and then we can evaluate that. Well, we know that the integral of e to the t is just e to the t, so this equals square root of 2 e to the t from 0 to pi, which is root 2 times e to the pi minus e to the 0, which is just 1. And that is our answer. Just to, there's a equal solution over here, done pretty much the same way, but notice we get to the same answer. So that's confirming or affirming. There's the solution that we just did. So let's do another one. It says find the arc length of the length of the arc described. So once you kind of get the habit of these, they're really easy to do. So dx dt is 2t, and dy dt equals 3t squared. So the arc length from 0 to 1 is the square root of 2t squared plus 3t squared squared dt. And now we simplify this. So we get L equals from 0 to 1 the square root of 4t squared plus 9t to the 4th dt. Well, to do this by hand, this doesn't integrate really nicely. So I think at this point, yeah, this you can't integrate by hand. It would simplify a little bit. Let's see, how could we simplify it? We could get L equals, we could pull a t out, so t times 4 plus 9t squared dt. And I think that's as far as we can go. So at this point, sometimes we need to revert to our calculator to actually find that arc length. That's fine. So let's change this mode. Even though we're dealing with parametrics, we're going to integrate something in function mode. And what we're going to integrate is, let's just do our original, the square root of 4x squared plus 9x to the 4th. And we want to integrate that from 0 to 1. So our lower limit 0, upper limit is 1, and that integrate, whoa, not sure what just happened there. Second calc 7, my lower limit is 0, my upper limit is 1. And so this is the arc length, 1.44. Okay, so that's that. Now let's look at an example of a BC problem where you have to do this. So take a second to read this problem. It gives us dx dt and dy dt for a position. We know that at time equals 0, our x position is 0, our y position is -4. It says find the speed of the particle at time t equals 3 and find the acceleration vector of the particle at time t equals 3. Well, to find the speed of the particle, we know that the speed in the x direction, so the speed in the x direction is just this. This is my meters per second in the x direction, and in the y direction, well, sine of 3 squared. So we're going sine of 9 in the y direction. So my total speed, if we think about x and y, my total speed is the sum of those vectors, or using Pythagorean theorem, my total velocity, or speed, my velocity is going to be the square root of 13 squared plus sine squared 9. Now we don't, that's not b. So we don't need to actually go through and computate that. but that is the speed of the particle at time equals 3. And what about the acceleration vector? Well, for acceleration, we know that the acceleration is going to be d squared x dt squared. The acceleration in the x direction, which is 4, and the acceleration in the y direction is d squared y dt squared, and that's going to be cos of t squared times 2t using the chain rule. So at 3 seconds, well, the acceleration in the xy direction is going to be the sum of these two vectors evaluated at 3. So 4 squared plus cos of 9 times 6, square rooted. And then find the slope of the tangent line at the particle at time equals 3. Well, let's do another page for that. That's a little ugly, but we can still read it. So find the slope of the line tangent. Find the slope of the line tangent to the path of the particle at time t equals 3. Well, that's the same thing. The slope of the line tangent to the path is dy dx. Oh, so it's not quite the same thing. So got it. So dy dx, that's the slope of the line tangent to the path. That we know that from the past. But so what we need to remember is that dy dx is dy dt over dx dt, which in this case is sine of t squared over 4t plus 1. And at t equals 3, we're looking at sine of 9 over 13. That's dy dx, or the slope of the line tangent at t equals 3. The next question says, find the position of the particle at time equals 3. So if we look at the x position, what we can do is we can integrate dx dt with respect to time from 0 to 3, and that's going to equal my x position at 3 minus my x position at 0. And I know my x position at 0. That's going to be 0. So if I integrate dx dt, so let's integrate for t plus 1 from 0 to 3. This equals 2t squared plus t from 0 to 3, which when we put in is 2 times 9 plus 3, 18 plus 3 is 21. And that equals x of 3 minus x of 0, but x of 0 is 0, so minus 0. So we get x of 3 equals 21. And now we need to find my y position. So my y position, using the fundamental theorem of calculus just in a slightly more sophisticated way, we can say that y of 3 equals the integral from 0 to 3 of sine of t squared dt plus y at 0. So I just reformed the fundamental theorem of calculus. And this integration, let's just do this using the calculator. So if we want to integrate sine of x squared, and we're going to integrate that from 0 to 3. My window's kind of crazy right here. So 0 to 3. This is going to give me my change in y, which is 0.77. and my y sub 0, well, that was given to me. That was -4. So my y at time 3 is 3 or -3.23. So I know my x position and my y position at 3 seconds. Easy. And then the last question that we are going to do says find the total distance traveled by the particle over the time interval from 0 to 3. So this is what we actually did today. To find the total distance traveled, that's just finding the arc length. So what we do is we want to find the arc length from 0 to 3. So that's going to be the integral from 0 to 3 of my arc length, which is the square root of dx dt squared. So 4t plus 1 squared plus dy dt squared. So sine of t squared squared dt. And so this, we can't really do this by hand. So go to our trusty calculator, and let's see. We want to integrate that. So we're going to get the square root of, and be careful with your parentheses here, plus sine of x squared. And we need to second insert parentheses. So sine of x squared squared, and then close the parentheses. I think that's good. So, and we want to integrate that from 0 to 3. So second calc integration, 7 from 0 to 3. And when it integrates, that will give us the arc length, which is the total distance traveled, so 21.1. And that's it for today. So arc length, including an interesting BC problem that we did using parametric equations. So our final answer, total distance traveled, and we used the arc length, was that area of the integration 21.1. 21.1 units. And we are done. That's it.